Hello and welcome to the Lockton Marine podcast. My name is Langeland Johannessen and this is a special episode. It was recorded live during the Houston Marine and Energy Insurance Conference on the 23rd of September, where I had the pleasure of joining a panel discussing merchant marine nuclear propulsion prospects and challenges. The session was moderated by John Preston, Chief Science Advisor at Quadrant Management, and my fellow panelists are James Watson, retired Rear Admiral from the US Coast Guard, and Steve Winston, Independent Senior Technical Advisor who joined the panel remotely. The audio has been cleaned up to the best of our ability, and we join the conversation as John is putting Steve's extraordinary nuclear power experience into context. Enjoy.
Steve's introduction, could have added the fact that he's built more nuclear power plants than anyone else in America. And I think he's tied for decommissioning nuclear power plants. He did 3 Mile Island #1, where he oversaw that. And so he's the guy to, any nuclear questions you have, he's the guy to focus them on. He's a chemi, nuki, and neuroscientist by training, so he's got a really interesting background. In Susan's introduction, when she talked about the 1973 energy crisis, it reminded me of a quote from Albert Einstein where he said there are 2 things that are infinite. The universe and man's capability for stupidity. And then he paused for a while and he said, well, I'm not really sure about the universe. Now, the way we responded to the 73 crisis was ridiculous. And maybe, Steve, I'm going to ask you to make a few comments about how we responded to the threat of proliferation when Jimmy Carter decided to make us use light water reactors. So say a few words about the percentage of fuel that's actually consumed in our nuclear reactors first, and then talk about how we should change that.
Sure. In 1977, Jimmy Carter decided that it was time to shut down nuclear fuel reprocessing. This is what we called it then. I began my career in 1973 at the Idaho Chemical Processing Plant in Idaho, what was then called the National Reactor Testing Station. It's now the Idaho National Laboratory. But in 1977, Jimmy Carter signed an executive order that basically shut down nuclear fuel reprocessing. It's starting to be revived. That the executive order is still in place. But the big problem is that it really put all of the PWR and BWR fuel in a situation where it had to be stored on site because there was no repository. And there still is no repository for intact nuclear fuel elements. And given the fact that the vast majority of the fissile material that's contained in those fuel elements is still there, they've been withdrawn from the reactors because of structural problems associated with the fuel elements themselves, or structural issues that makes it not safe to continue to operate with them in the core. That means we have an awful lot of spent fuel assemblies that are stored around the country. And so hopefully we'll soon be able to begin processing fuel. Recycling is the new word. Clever idea. Perhaps the liquid metal and molten salt reactors that actually have the fuel contained within instead of a solid matrix, a molten material, may enable us to more easily recycle, and that I think is potentially the future with regard to marine propulsion using perhaps molten salt reactors as an excellent candidate.
Yeah, so we probably have about 150 years worth of all of the U.S. power consumption that's currently being stored as waste radioactive material, and one of the ways that we might be able to rapidly move the nuclear industry back into revitalization might be to make what's called radioisotope thermoelectric generators, which is what NASA's been doing. Actually, Steve built them at Idaho National Labs. So if you look at Voyager 2, which was launched in 1977, 2 billion miles away from Earth, still sending signals back. It's powered by a small amount of radioactive material that's decaying over a 70-year lifespan, and they're using the heat to generate electricity. We're thinking that we're going to try to do that next year, to have a first demonstration of a commercial application of that kind of technology. But that's a different subject. I also wanted to just open your eyes a little bit to the fact that 90% of all the engineers and scientists that have ever lived in the history of mankind are alive today. And the rate of change of technology is accelerating. You know, when I was handling MIT's inventions, we got 2 inventions every day, covered a wide swath of technologies, and that whole thing, in fact, when I left that office, a study was done on MIT alumni-founded companies, and they found that if it was a separate nation, it would be the 9th largest economy of the world. And I don't know if that's still true, because NVIDIA was not founded by MIT alums, but Moderna was. So who knows? It's probably way up there somewhere. I think that maybe what I'll do is shift gears a little bit. I'm going to sit here and I'm going to throw some questions at our 2 speakers here. But I also want you guys to feel free to raise your hand at any time, and if I can see you, I will let you ask questions also. So why don't I start, Jim, with you? And so could you give us a little bit of a rundown on the current state of U.S. Merchant Marine?
Sure, John. Well, I happen to have just been a co-author on a book on this subject, and just to give you sort of the headline, the title of the book is 0.4. 0.4 is the percentage of U.S. flagships in the population of world ships. And we're talking about seagoing ships, excluding the barges and tugs and the small stuff that really doesn't go to the high seas. But that's 180 ships out of 55,000 ships in the world. So the largest economy in the world has one of the smallest merchant marines in the world. And it's been going that direction, smaller and smaller, really since the end of World War II. So, and then this part of this is by our national policy. I think we wanted to promote globalism, promote shipbuilding, ship operations, mariners from any country in the world. There's a World Maritime University in Malmö, Sweden, that we were supporting to make sure that we were really truly extending the ability to have a maritime career to virtually everybody in the world. But I think now there needs to be a close look at, do we like where we are? Is just 180 ships adequate? Now, just to put a little bit more details on that, out of that 180 ships, 100 of them are in purely domestic services. Okay, so these are the seagoing ships that are required to go to Alaska, Hawaii, Puerto Rico, Guam, and coast-wise with significant amounts of cargo, all your tankers, for example, that go up the East Coast. So that really means that there's only 80 ships that are truly in international trade. They're carrying our imports and our exports into and out of the country. And almost all of those are subsidized. So they're in a maritime security program, a tanker security program, a cable ship security program, or they're one of the 4 ships that is currently working for the Department of Agriculture or the USAID to carry grains in the food programs that we have. So there's no particular plan right now to change the status quo. What we're hoping we'll see in the next few months is a report from the Center of Naval Analysis that was mandated by the U.S. Congress in 2023 to do a study on the situation, give that to the Maritime Administration, and then we would hope to get a maritime strategy from the Maritime Administration sometime next year.
Great, thank you very much. The public attitude on nuclear has been changing quite a bit, and 1997 when I was asked to advise the White House in preparation for the Kyoto summit. About 70% of Americans were anti-nuclear, and today it's over 70% pro-nuclear, because they can see what's happening on climate change. And when I went down to the White House, my first 4 slides were on nuclear, and I was politely asked to go to slide 5 and skip over the discussion of revitalizing nuclear. It's changing rapidly right now, and maybe Anders, could you give us a little bit of your sense of the way nuclear commercial vessels are being discussed in the insurance community?
Sure, thank you. So I think the important thing is that they are being discussed. It's on the agenda today. It was on the agenda when the international group of P&I clubs met in July, and last month when the Association of Nordic Marine Insurers met, they were talking about nuclear-powered ships. So it has made its way onto the agenda, and I think that is partly because we are, as an industry, are being dragged along by significant players, both on the ship owning side and on the shipbuilding side, where there is an increased focus on the opportunities that come with nuclear power vessels. But also, it is what you just mentioned, the fact that public perception is changing. And I think, speaking of public perception, I think the survey that you referred to, that there are 2 very interesting takeaways. One is that half of the people asked who were in support of nuclear power actually thought that nuclear also came with significant greenhouse gas emissions. So there is a misconception that it's not clean, which it is, and you would have to think that once that key piece of information is known by all, that the approval rate will go even higher. The second thing is, if you look at the trajectory of public opinion on nuclear, it takes a dip in 2019 and 2020, which is around, and this is purely speculation on my part, but it's around the time where the Chernobyl miniseries was available on TV, it just shows how fickle this is, right? But I will say that using Chernobyl as an argument against nuclear-powered vessels and the technology that we have in 2024 is like using the Titanic as an argument against going on a cruise next summer.
And also, probably we could add that Russian-built nuclear reactors, and I'll turn to Steve maybe to comment a little bit on that. Prove Einstein's quote about stupidity, mankind's capability for stupidity being infinite. But Steve, do you want to make a comment on that?
Well, I guess there's a couple of things that I wanted to bring up in addition to the fact that I think that the proving ground for maritime nuclear propulsion is probably floating nuclear power stations, and the Russians actually have one in operation. It actually ran over on costs. I don't think there's a reason why we should run over on costs. But coming back to the reason why we should be looking at nuclear propulsion of merchant marine ships, 3% of all global greenhouse gases come from the combustion of bunker C. And a substantial portion of the PM 2.5, that's the particles that are suspended in the air that are less than 2.5 microns and cause the most health damage. A substantial portion of that also comes from the combustion of bunker C. And obviously, modern ships are too large to propel exclusively with wind, and they're too large for us to deploy solar arrays that would be able to propel them. So we need to look at realistic opportunities. One of the things is simply economic, and that is a nuclear ship can, if it's designed properly so that the hull speed matches the power available, it could potentially cruise at in excess of 25 knots. That's almost twice the speed that you can operate currently. In other words, one vessel may serve the purpose of 2 with the current situation. Second consideration is the fact that you don't displace cargo because we don't need to carry fuel. And depending upon the type of vessel, that means an increase of about 20% of the payload that you are able to deliver. So with those compelling arguments right there, from an economic perspective, there's a strong driver. And that means that there are costs potentially that don't have to be passed through. And in the case of cruise lines, that means a savings to the bottom line that's rather substantial. If you look at the difference between, and I'll just use an example of a Maersk Class E, the capital cost for a power plant on the order of 100 megawatts, which is roughly the order of power necessary to propel the ship, about 110,000 horsepower. The cost for that in bunker C is about $64 million per year in operating costs. Nuclear fuel, the same power and twice the speed, would cost you about $4 million. So there's a huge imperative there. The second thing that I think is important to look at is we can't just put a bunch of nukes on a bunch of ships and take off. And this is something that Jim will have to talk to, and that is the fact that not every port is going to welcome with open arms immediately the idea of a nuclear ship coming in. A nuclear-powered ship. So we have to deal with the Coast Guard issues and the emission issues in the ports around the world. And perhaps most importantly, and this is what will be, I think, of the most interest to most of the viewers here, is today we need to figure out how to not only insure the cargo in a nuclear ship, but also to address the excess liability associated with operating that, and that's something that Anders can address. And then there's the licensing issues, and those are quite extensive, but I think are eminently addressable. But perhaps the most compelling thing from a U.S. and Western world perspective is the fact that there is no doubt that the Eastern Asian countries will move forward rapidly, particularly China, in the deployment of nuclear-powered merchant marine ships. And that poses potentially an economic disadvantage for Western countries that don't have an equal capacity. So with that in mind, that kind of sets the stage as to why it's so important that we talk about this, and particularly because everything starts with addressing the liabilities question, why the insurers are potentially the long pole in the tent, or the long tent at the pole, I guess. That's important. Go ahead, John.
Okay, thanks, Steve. And so, Jim, that kind of leads directly to you. Would you like to say a few words about the current state of small modular nuclear reactor industry as it relates to propulsion? But also, could you pick up on Steve's point on the ports, the permitting of nukes coming into ports?
Sure. Well, I think I'm a marine engineer and also a Coast Guard regulator, and I think the big change here with the technology that we're seeing in the small nuclear reactors and small modular reactors is the safety factor, and the fact that with the type of containment systems and the fuel that's being used, there's a whole different ballgame in terms of the area that constitutes the safety area around the reactor, and it's very, very possible for it to just be the ship itself, as opposed to when you think of a power plant and the safety area around a light water reactor, and we're talking about completely different technology even than what the Navy's been operating for a half of a century. So I think that is a game changer for the potential of having reactors on ships. Now, back to your question about ports. It's very interesting. I did a little research, and in 1962, there was a international convention on the liability of nuclear ships, and that's still in effect. In 1968, there was safety recommendations that came out from the International Maritime Organizations on the use of ports by nuclear merchant ships. We're talking merchant ships here, not navies. And then in 1981, there was a code for the safety of nuclear merchant ships. The United States actually led the world with the design, construction, and operation of 10 years of the nuclear ship Savannah. That was built in 1959 and started operations in 1962. And we have so much better technology now that it shouldn't be that difficult to pick up where we left off and move on. And I think that that is what needs to be done. And just reference back to this strategy that has a timeline now that will be coming out from the United States government. And of course, it's going to need probably some legislative and some investment follow-ups to make that executable. But I think that we're in a position that we have not been in this country for many years to take advantage of these technological and political changes that have been occurring and that will ignite potential for a whole new fleet of U.S. flag vessels with U.S. merchant mariner crews.
So before go ahead, Steve.
I was going to amplify the point that Jim just made about the difference in technology. Specifically, if we were to use something like a molten salt reactor, whether it's a fast chloride reactor like Core Power is talking about, or just a regular live molten salt that is a fluoride-based, sodium fluoride-based reactor system. First of all, from a technological perspective, they shut down when they get too hot. That means there's a negative coefficient of reactivity with respect to temperature. So a core meltdown would be absurd because the core is already molten. So they're extremely safe, especially in a situation like this. Unlike a sodium-cooled reactor, what a liquid metal fast reactor is, you wouldn't want to put sodium out in the middle of the ocean as sodium metal because it reacts so strongly with water. So either a lead-based or a molten salt-based, that is a sodium chloride or sodium fluoride reactor is very safe in this context, and it's extremely simple in comparison to the complexity of a PWR, a pressurized water reactor, or a light water reactor. So the technology, as Jim was saying, is dramatically different. It's much, much easier to operate. It's much simpler. Now, the question is, how far along is it? The first molten salt reactor system that was developed successfully and operated was a molten salt research reactor at Oak Ridge, Tennessee in 1966. So there's a wealth of information that's available on all the licensing issues. But that still means that we have to address those licensing issues in a meaningful and significant way. So the question about are they safe, the answer is yes.
Yeah, so maybe before I throw a question over to Anders, I'll ask the audience. There are three dominant ways of producing electricity, ignoring solar and wind and the renewables that are coming up. So you've got natural gas, you've got coal, and you've got nuclear. Which one do you think is the least safe, the most deaths per megawatt hour produced? Now, I'll say, let's throw up our hands first for anyone think it's natural gas? Okay, how about coal? Okay, how about nuclear? Okay, so we got zero nuclear, zero natural gas. You guys all got it right. It is coal, which is 10 times worse, according to an MIT study, 10 times worse than natural gas in terms of deaths per megawatt hour. Much of that's from black lung disease for the miners and so on, and transportation issues, accidents on rail and so on. Natural gas is next, it's number 2, which is 10 times worse than nuclear. So in terms of the safe, and you look at, by the way, the U.S. Navy has been operating nuclear ships for 50 years now, very safely, with no incidents. And the only incidents I can think of on nuclear ships are Russian. But like I said, we have to ignore the infinitely stupid. So, Anders, let me turn to you and ask you to address some of the issues that Steve threw out, which are the greatest challenges for the insurance industry before we can actually see nuclear-operated propulsion system.
Right, thank you. So to answer that, let's separate between hull insurance, so insuring the ship itself, and then liability, so insuring whatever damages it can cause. So from a hull perspective, the solution lies within the industry itself. Today we exclude what is commonly known as the race to perils where nuclear is one of them. That was not done for the purpose of not allowing nuclear propelled vessels. It was done for a completely different reason. It was to deal with the potential aggregation that comes from a catastrophic nuclear event that originates perhaps outside of the vessel. So I think the solution within hull insurance lies within the industry, and I'm speaking to people within the industry. That is something that we could, that it seems that there is consensus that could be resolved. On the liability side, it's more difficult because the ability to provide liability insurance relies heavily on the vessel's ability to limit its liability. And if you look at the Convention for Limitation of Liability, it excludes nuclear, right? And if you look at something like the Vienna Convention for Civil Liability, that puts the exclusive liability for an event on the operator. So in order to be able, as an insurance industry, to fully come to terms with this and keep up with what's happening on the technological side, there has to be a cooperation between regulators, the IMO, governments, the shipping industry, and insurance. But I think there is movement in that direction. It's just something that takes a bit longer to achieve.
Great. And so Jim, I want to talk a little bit about the economics. Now Steve already kind of alluded to the fact that the economics of running a Maersk class ship is about $64 million per year of bunker C, and the equivalent nuclear fuel in a let's say a molten salt reactor would be about $4.5 to $5 million per year. That would be 100 megawatts of electric, which means 150 to 70 megawatts of thermal. So maybe you could say a few words about the economics of international shipping. Maybe you just agree with what Steve said, or you can elaborate a little bit on it. And particularly, I'd like you to address the issue of how many ships we need and what speed do we operate at, and issues like that.
Sure. Well, you think about the economic drivers here. Certainly, the life cycle operating cost is what the ship owner is going to be thinking about, and so that's primarily your capital investment up front and your operational costs downstream for the life cycle of the ship. But an emerging issue these days is the price of carbon. There's already an EU tax on the amount of carbon emissions coming in and out of Europe.
There's going to be a phenomenal presentation on that a bit later. So
good, because that's a critical thing.
Do that presentation.
Yeah, I might.
So don't miss this talk later.
So you can look backwards and compare. What primarily for a nuclear powered ship, it's the capital cost. It's obviously more to have a reactor in a ship than a off the shelf diesel engine that burns heavy fuel oil or distillate fuel. But you never put any fuel in it, and you're never going to pay any carbon costs. And then you look at the potential for that cost of fuel going forward. You could buy a ship, and there's ships being built now, both the operating off of LNG and off of diesel fuel, where the owners, a ship, remember, lasts about 25 to 30 years. So the target for being zero carbon in maritime is 2050. So the ships that are being built now will need to meet that. So those ships that are installing the diesel engines and the LNG fueled engines are anticipating that there's going to be a drop in fuel to replace those carbon emitting fuels. Where you look at the cost of those fuels compared to the cost of the fuel now, that's going to be the really big driver to that life cycle cost of those traditional ships, whereas you pretty much have a fixed known number for a nuclear ship. Now I brought this model here because There's ships being designed right now. And another feature of the economics is the speed. So, and also the size. One of the things that we've been experiencing over the last several decades is ships are getting bigger and bigger and bigger. Well, this is because of the current economics of operating ships. Well, the unintended consequence for our country, since we're not really benefiting from being ship builders or even ship owners, is when these other operators design and build huge ships, we have to raise our bridges, we have to dredge our ports, we have to buy these cranes every time they increase the size of the ship. So it's a great business model. It's something that Bill Gates figured out back in the early 80s. You sell a product that has to be renewed. That's a great model. Okay, that's what we're dealing with as importers and exporters in this country, and as taxpayers who are paying for all of these things in response to this maritime industry that we don't have any control over. A nuclear ship that goes twice as fast as another ship can replace two ships with one ship, because it can go back and forth in the same time a single transit.
Yeah, and have greater flexibility at which ports it stops at, because it can carry smaller cargoes. So it's more flexible.
Exactly. So now if we instituted that new paradigm in ship design and operation, we could rearrange the supply chain system of the world, or at least for our own purposes here in the United States. So the other aspect is the shallow draft and the dual purpose use of ships in the event that we need to have military logistics move halfway around the world to, say, small Pacific islands, or places where you don't have these infrastructures that are required when you have deep draft gigantic ships.
Okay.
So those are some of the economic drivers. Most of, I think, the economics for owning a U.S. flag vessel is going to intersect with our national security needs as well.
So John, could I address the capital cost for a second?
Yeah, sure. And maybe you could say a few words about the NRC and the 1 year mandatory. I'll let you cover it.
Well, specifically, there's a question about the cost overruns that have become spectacularly notorious in the nuclear industry on constructing new power plants. And it turns out that a significant portion of those costs is associated with establishing the site and licensing the site, in addition to the licensing of the technology itself. It turns out that a significant portion of that cost is associated with seismic criteria, which don't apply at sea. So taking those costs out and the capital costs associated with the concrete and steel necessary to build a plant on land, that's a significant cost savings there. Another huge percentage of the cost associated with building a power plant on land is associated with the carrying costs and the delays that are associated with getting the site approved. And that includes these, in the United States, the environmental impact statement, which has a 1 year statutory requirement built in already. And then the NRC licensing process in the United States has built-in comment periods in which the proposer has to address comments of those who may have questions or reasons to object to the construction of the power plant.
Yeah.
If you eliminate those costs, then you take advantage of the cost that you can cool a power plant a lot more efficiently at sea than you can on land, because there are limits on how much temperature rise can be tolerated in a river, stream, lake, or estuary. You can actually save an awful lot of money associated with the waste heat disposition. So it's credible for us to talk about building a nuclear power plant that costs on the order of $1,200 to $1,400 per installed kilowatt. That means that for a Maersk Class E, coming back again to that example, and I'm not trying to pick on Maersk, is that you could potentially build that power plant for less than $100 million. And then the payback, when you're looking at a difference between $64 million and $4 million per year, is pretty rapid. But that means that you get through the first licensing process as quickly as possible. But the bottom line is the capital costs are not extraordinarily different than the capital cost of getting 110 horsepower diesel.
Yeah. Thanks, Steve. Now, because of time, we're the only thing separating you from lunch, and so we're going to. I promised to finish by 12:05, and so maybe this will be the last question. I'll send it over to you, Anders, which is, to talk about what are the forces working for insurance to embrace, nuclear, or maybe you can also talk about the forces again of evil.
Sure. So if you look at the forces working for this development, I think you touched on it. The regulations, the net zero pressures that are coming both from the EU and the IMO, and will be coming from the IMO. Also the fact that insurers and the whole value chain has to participate in that journey towards net zero means that we have to embrace new technologies. And it is really, really hard to envisage net zero shipping without thinking about alternative fuels. And if you think about those alternative fuels, the nuclear looks like a very nice prospect. In terms of the forces working against, obviously there will be those public perception issues, and it's fickle, so the first incident will be very difficult to handle. I think there's one of the more popular questions that come up in the context of nuclear and insurance is the one of piracy, which I think has to come from a place where people think that these are floating bombs, which they are not. And again, I think you could do a lot more damage with a hydrogen-powered ship or an ammonia-powered ship than you could do with a nuclear-powered ship. So yeah, it's all about that journey to net zero, and this is a very important component.
Great. Well, thank you very much. We're kind of at the end of unless there's one urgent question coming out of the audience, I think we'll call it quits right now. But I want to thank the.
We have a gentleman down in the corner.
Yeah, please. Yeah, so maybe Steve, I'll repeat that question for you, which is at the end of the ship's life cycle, or even at the end of the fuel life cycle, what would happen? Let's use the example of a molten salt reactor. What would happen to the fuel? And I know that some of the companies like Thorcon are doing continuous refueling over a 30-year period where they never take anything out other than the gases and a few other things. But maybe you could say a few words about that.
Sure. Just quickly, the fuel itself gets moved from reactor to reactor because it's molten salt. And because it's replenished continually, it's in as good a shape as it was when it started. So it goes on to the next reactor. We will it would be advisable, I think, to replace the can because it suffers from what's called neutron embrittlement over a period of time. And there are corrosive fission products that have to be dealt with that can create problems with the reactor vessel itself and the heat exchangers. So that primary reactor vessel and the primary heat exchangers would be taken out of the ship on probably a 5-year basis, perhaps a 10-year basis. So when you hit dry dock, you pull the can out. You take the fuel out first, obviously, and then you use that to fuel the next reactor that you put in there.
Yeah,
so you would be continuously processing the fuel, separating out fission products. The gaseous fission products are taken off continuously and stored. And then the activated materials, that is the primary vessel and the primary heat exchanger, would be disposed of as low-level waste. And now there's a mistake that's often made, the presumption that the low level means low radioactivity. This would be fairly highly radioactive, but the quantity of it is relatively small, and the half-lives of the material that it contained, the activated half-lives, are such that you can dispose of them in what are called low-level waste disposal sites, one of which is in Texas in the United States. There's also another in Clyde, Utah. So it's not considered high level. That is, high level is reserved for things like nuclear fuel assemblies.
Okay. So the short answer is You will have maintenance primarily on the metal components around the nuclear fuel that will have to be replaced periodically. But if you look at the bigger scheme of things, that maintenance is lower than you would have in a typical diesel engine or in a gas turbine power plant. So the ongoing operating costs are comparable from a maintenance point of view and much lower from a fuel point of view. And so I think at that point we are going to call it quits. Thank you very much, and thank you to Anders and Jim for your comments.
Thank you for listening, and we look forward to welcoming you again soon to the Lockton Marine podcast.